Okay, give yourself a pat on the back. We made it to the last hypothesis test. We'll be running a chi-squared test today. I want to give you the most important features of what's called the chi-square distribution and this chi-squared test for independence. We're not going to be doing a lot of by-hand calculations with this. We're going to go straight to the punch, which is how do you do it on the software and how do you do it on the graphing calculator, okay? Just a little bit of light intro. So, characteristics of the chi-squared distribution, it is unlike the normal distribution and the student t distribution in the way that it is not symmetric. However, one way that it's like the student t distribution is that its shape depends on its degrees of freedom. Okay? And as the degrees of freedom gets higher and higher and higher, it becomes more nearly symmetric. The values of the chi-square are non-negative, and that is the values of the chi-square are greater than or equal to 0. Okay, let's actually take a look at a chi-square distribution. Okay, you can see here we have a chi-square distribution with various degrees of freedom, and you can see, as I'll highlight, as the degrees of freedom here, once they hit about 30, that curve is becoming more and more normal. Here in orange you've got this degrees of freedom are only 10, and you see a right skew. So it is a skewed distribution, tail is to the right. But as those degrees of freedom, tend towards, greater than or equal to 30, you're becoming more and more symmetric, okay? Okay, now a little bit more background of what we're about to do. We're going to run what's called a chi-squared, let me change my marker here, a chi-squared test for independence. It's used to determine whether there is an association between row and column variables, okay, in a contingency table constructed from sample data. The null hypothesis is that the variables are not associated, in other words, that they're independent. And the alternate hypothesis is that the variables are associated or dependent. So, just to clarify that, the null hypothesis is always that, is basically, in easy words, there's no association between row and column variables, and H sub 1 is that there is an association between row and column variables. Okay? So be a little more formal here. In other words, in a chi-square independence test, the null hypothesis is always that the variables, row and column variables, are independent. And the alternate, this should be an H1, the alternate hypothesis is always the variables are not independent. So you'll know how to, I call it stating the ho and the ha, the null and the alternate hypothesis. You'll know how to state those. They're always sort of etched in stone. Okay, so now we're ready. Let's just go ahead and perform this chi-squared test for independence. In a poll, 883 males and 893 females were asked if you could have only one of the following, which would you pick? Money, health, or love? Okay, the responses are presented in this table. So like 82 men said money, and 446 said of the men said health, and 355 of the men said love. And 46 women said money, 574 women said health. So basically majority of men and women, said health. And funny they didn't pick love, but and 273 women said love. Okay, question. Test the claim that gender and response are independent. That basically means test the claim that there is no association between row and column variables, right? Or is there an association between row and column variables, between gender and what they would pick? So we know the null and research hypothesis now. Okay, so we want to know whether gender and response are dependent or independent. So the hypotheses are as follows. H naught would be gender and response are independent. H sub 1 would be gender and response are dependent. Our level of significance, we're going to run this at alpha equals 0.05. Okay, what I have here is a table of expected frequencies along with actual frequencies. The expected frequencies were computed using the book method, which is, the book gives a lengthy explanation of that. I'm not going to go into that, but they're given in parentheses in the table below along with the observed frequencies. So this is what we actually observed, and this here number would be what's called the expected frequencies. Okay. Now, if you're wondering where that number came from, there's a long derivation of that in the book. I'm not going to go into that now, though. Something that we should be aware of, though, is since none of the expected frequencies were less than 5, the requirement for goodness of fit test are satisfied, so we're okay to run this chi-square test, right? The test statistic is as follows. So notice it's the observed minus the expected. So basically a chi-squared test statistic would be summation observed minus expected, whole thing squared divided by the expected. Okay. Now, if you're, so you can see, you know, if you go back and look at that previous table, that's 82 is the observed number of men who thought something, and 63 was the expected, right? So you do that basically for each cell count, and that's why you see the dot, dot, dot here, okay? And basically, sum that all up, eventually your chi-squared test statistic is going to be, you know, 36.82. The reality of it all, though, is that, you know, software is just going to spit out this test statistic, as we're going to see in a moment. I just did want to mention that, you know, if you are taking the classical approach to a chi-square test, there were 2 rows and 3 columns on our contingency table. So the degrees of freedom are basically your number of row variables minus 1, you know, and your column variables minus 1 times each other. So basically 2 minus 1 is 1, 3 minus 1 is 2. So there's 2 degrees of freedom. So the chi-square with 0.05 alpha, with regard to 0.05 alpha and 2 degrees of freedom, would be this number right here. So this question of, you know, does our test statistic live far enough out in the tail to make you reject the null? And we just computed our test statistic. It was way out in the tail, way beyond 5.99, okay? So again, the sort of the old-fashioned way of doing things was to compare your test statistic to some critical value of chi-square with regard to alpha. So our test statistic was 36 point some. The critical value was 5.99. We reject the null. Again, that's the old-fashioned way of doing it. Now let's take the p-value approach and actually run this on the TI, which is what you were all waiting for, I'm sure. Okay, so if you're running this kind of test on a graphing calculator like I'm about to do now, you're going to want to go into matrix. Okay, you're going to want to slide over to edit. Your dimensions are hit enter for matrix A. The dimensions are 2, enter, 3, enter. Okay, dimensions are 2 by 3. You're going to type in all the information, all the cell counts like 82 and 446, and you see where I'm reading that from, right? And then 355. Okay, and then 46, and then 574, and then 273. Okay, so I put all that information in the calculator. Then, the fun part, you're going to hit stat, you're going to slide, let's see if I can actually make this calculator bigger so you can see it now. Okay, stat, slide over to tests. Now you know all these hypothesis tests are under this window, right? Slide down to chi-square test. And that's why I say software can do this, you know, in under 30 seconds. Hit enter. And it says observed, and it says matrix A. See, it knows that you put the observed values of what you saw in matrix A. Expected, it has done that for you. It's created another matrix B that has the expected counts. So it did that sweat equity for you. Calculate, hit enter. So it spits out the test statistic, you know, of 37.5, and the p-value, notice that p-value, 7.14 times 10 to the negative 9th. That's a very small p-value. So it's way less than the alpha. So again, I just want to zoom in. Notice that chi-square. See if it'll let me write on here. Notice that chi-squared test statistic of 37.5. Oops! I just realized that that chi-squared test statistic was 37.5, and when we did it by hand, it was slightly smaller than that. So I realized I entered one of the data wrong. So go back into your matrix and check. So 82, 446, 350. Yeah. that should have been 574. So you'll always notice if, what you got by hand. Let me shrink this again. So basically that should have been 574 for that entry. What you got by hand doesn't match, what the computer said. And this one should have been 273. Okay, let's run that again. So we'll do stat, slide over to tests, slide down to chi-square test. Should have been that one. And now let's try that again. Calculate. There we go, 36.8. Now let's see if that matches. 36.8, there we go. So, again, in other words, if I like to make sure that whatever my calculator is spitting out is what I would get if I were to do these formulas that are in the book, right? So 36.8. And again, the calculator gave us that very small p-value. Let me go back to that. P-value, now it changed since I had to fix that data entry issue, but it's still scientific notation. It's 1, and then it says e negative 8, right? So that's 1 times 10 to the negative 8, so very small p-value. Now we'll do decision and interpretation, okay? So just to share that with you, which I'm sure you're all familiar with by now. Since the p-value, which is very small, is less than the level of significance, we reject the null hypothesis. And if we reject the null, we're in favor of the research, which says that an association does exist between row and column variables. Okay, so to see the relation between response and gender, we would have to draw graphs of conditional distributions of response by gender. We're not going to go into that segment. Our course ends pretty much right here at the chi-square test, but good luck, and perhaps we will take a look at running that on Excel as well. Okay, so just for grins and giggles, I pulled up the sheet here. You can see, let's see if I can make it in range for you to see this on the screen. Oops, let me shrink a little bit, move that over. Okay, so you can see I just pasted in. Now I didn't get too fancy because you know what the titles are already. Money, health, love. So you see my spreadsheet here. I just put 82, 446. I could have scooted things over, and just want to talk about what to highlight and how to do this on Excel. So you would go to add-ins, Megastat, assuming you have that Megastat add-in for Excel. It's very simple. You just go down to chi-square crosstabs, right? Contingency table. Just go like that. And then when it says input range, you go here. You highlight all your cells of interest. Okay? And you just click on chi-square. If you want to see the expected values or any of this other information, if you want to see this or this or this, that's fine. Hit OK. And it'll spit out, the observed and the expected values, which I think is neat because it verifies what how the book tells us to do it by hand. But then notice, if I can zoom in here for you, notice it's going to give you the chi-squared test statistic. So note to self, it gives you the test statistic, and it's going to spit out that p-value, the same one we got on the graphing calculator. So we like to verify, whether we do it on the graphing calculator or by hand or Excel, we're getting that same p-value and that same test statistic. Okay? All right, good luck, everyone.